Hello everyone, and welcome to the second lecture of Digital Elevation Models and Application course. In this particular lecture, we will be discussing various techniques to generate digital elevation models. So, there are going to be 3 lectures on this topic, but in different lectures we will be discussing different techniques to generate digital elevation models. In this particular one, we will be discussing a technique which is based on the interpolations. Earlier it was one of the most popular technique, and still many people are using, depending on the data which they are going to use, depending on the project. Accordingly, we choose the appropriate technique to generate digital elevation models. As we know that digital elevation models can be created through number of ways. Different techniques are there, but most preferred one is the method of generating DM, is the remote sensing based. So these are the ways of we can create digital elevation models. The earlier we used to have survey topo sheets like Survey of India topographical maps using contours or point heights. We first used to digitize and assigning the elevation values to these point heights or contours as a attribute value, and then using these values we used to create surfaces which are estimations of values through spatial interpolation technique. So this is one of the popular one is a spatial interpolation technique. In this particular lecture we are going to discuss in detail about how different interpolation techniques can be employed to generate digital elevation models, what are the limitations, accuracy issues, and some other applications. Other way of creating digital elevation model by using stereo pairs like might be available from Spot, our own Indian satellite like Cartosat, etc., which is nothing but a remote sensing method, and that too based on photogrammetric technique. This is also popular. This will be also discussing in subsequent lectures. There is also one technique a few years back I have developed, which is based on thermal infrared of a hilly terrain, but at a relatively low resolution. But this can give you some advantages as well. So that will be also discussing in brief in subsequent lectures. Then radar data pairs, very popular technique nowadays. Either you can use for example NVSat data or Sentinel data, which is still operational Sentinel, and employing this INSAR or SAR interferometry method. One example, in previous lecture we have seen about the SRTM digital elevation model for 80% of the globe was generated using this INSAR technique, which is purely a remote sensing based technique. Now LIDAR data again is a remote sensing method, but the most popular one are nowadays based on either on aircrafts or on ground based LIDARs can also be used to create surface models. So that we will be also discussing very briefly. So let us first come to this spatial interpolation technique using either contour data or point heights. As you know that contours are representing the equal heights or heightal contours, we say them. If you see from vector data structure point of view, then these are the polylines, and polylines are having in between various nodes, including 2 end nodes, begin node and end node, and in between various internodes are there, and these nodes are assigned elevation values, and they make basically a contour line. So contour line is also made from points, and of course point heights can also be used to create digital elevation models using spatial interpolation techniques. Various softwares will use directly through point side you can create surfaces, that is the digital elevation model through interpolation, or some software will also allow you to create DMs using contours. But what these software will do in the background, first they convert your polygon or polylines to point, because these polylines are also made from point, and then create the spatial interpolation. So why? Because for interpolation the data has to be supplied in the form of point data only. So line or polyline can be converted to point first and then can be used to create surfaces. Basically the concept of this spatial interpolation is based on a sort of belief, and belief is that if you are having two observation points and in between you do not have any observation, but if you believe that they are linearly related or non-linearly related, then a value can be estimated between two observations. So using this belief, depending on the terrain conditions, one can create a surface. So from point data, which is a discrete data, vector data, a continuous data or raster data can be created, which is nothing but a digital elevation model. So spatial interpolation techniques basically converts your raw data into a useful information, because once surface is created, a digital elevation model is created, then various products can be generated. As mentioned also, that a DM, digital elevation model, is a storehouse of information. Various types of informations can be extracted from digital elevation models, which we will be seeing in subsequent discussions. So by adding this greater informative content and value, instead of just using point data, which may not give you that level of information as a surface or a digital elevation model can provide. Also, when we convert this point data into surface, that means from discrete to continuous, we can also see different patterns which are present in your surface. Like example earlier also shown, that in a digital elevation model can tell you which are the areas which are having the ridges or hilltops, which are the areas having valleys or drainage lines. So these patterns can be revealed using digital elevation model or using surfaces rather than using discrete data, that is point data. Also we can see the trends in the data. Anomalies might be suddenly you are having a hill or maybe ridge or maybe a depression. Those things can also be, anomalies can also be seen. Otherwise in a simple point data plotting you may miss all these things. And also it provides a check to human intuition, because between 2 points, as given the example, if you do not have any information, then there are techniques to fill that information, to estimate the value, and therefore instead of using human intuitions, we use the mathematical algorithms to estimate the values, and these can be also checked later on employing by differential elevation, differential GPS or some other elevation models, and then can be compared, maybe a low spatial resolution digital elevation model, and using random point we can compare and see that how close they are with the reality. So it really in that way very useful, by helping in situation where I might deceive, where we may not see. In a typical, this is the typical flow process or flow diagram of the processes which are involved in while creating a digital elevation model using topographic maps. The first step in topographic maps, if they are not already available in digital form, nowadays a lot of topographic maps are also available in digital form. So what we need, basically we need the contours or point heights extracted from those topographic models and topographic maps. If they are already not available, then the first step is going to be the scanning using a flatbed scanner or some roller scanners. Then we do the georeferencing that means bringing the geographic coordinates into your scanned image, because that map or scanned image of a map will be in a geometric coordinate. So, by employing georeferencing technique, which has been discussed in length in detail in the GIS course, so that can be used here, and then we can digitize individual contour lines, point heights, and then we get these two outputs, points or lines. As I have already told you that directly from lines, most of the softwares, especially GIS software, will not allow you to do the interpolations. So, lines can be converted into points, and you can also bring GPS data, especially the differential GPS data, for verification or validation of your interpolations. So, that is also there. Finally, you can create the interpolations. This DGPS data can also directly the data can come as in point forms, and that data can be used to create digital elevation models through spatial interpolation techniques. So, this is how the entire process of creating digital elevation models employing spatial interpolation techniques using topographic maps. This was very popular before we got this digital elevation models global, especially I am talking like SRTM or Ester GTM. Now, as we can see here that these are the contours represented, and the same contours can be used to create a surface that is nothing but a digital elevation model, and this is how it will look. Now, as mentioned here that the surface or DM will reveal the patterns. So, here we can see some patterns and some anomalies and other things can be seen quite easily as compared to contours. Now, in spatial interpolation, so first we will look the definition, then various types of spatial interpolation techniques, and then some limitations, accuracy issues and other things. So, let's see first how we can define the spatial interpolation, which is a procedure of estimating the value of properties. Now, property here may be elevation, may be concentration of certain chemicals, or maybe water level and so on at unsampled sites, because for that we do not have the observation. This is key point. Why we are doing interpolation? Because we are doing interpolation because for all points we do not have the observation, and the observations are not available at regular intervals. The observations are available at irregular intervals, and therefore we want to create a systematic surface where each cell will represent a certain value, maybe elevation value. So, that is why the spatial interpolation is the procedure of estimating the value of properties at unsampled sites within the area covered by existing observations. So, of course, this interpolation also includes some extrapolation as well beyond the area, but there the errors will be very high. So, that is why in the definition it has been mentioned within the area covered by existing observations. If we do not have the observation and still you go for interpolation, in fact that will be called an extrapolation, and extrapolation can bring lot of errors in the data. But sometimes for the margin or boundary areas we also go for extrapolation, which we will see in the demonstration while using a software. Now, what basically interpolation is doing, it is predicting the value for a cell of a raster or a DM from a limited number of sample data points. So, you are having some points which are randomly distributed in a space or in a given area. Now, using these points, it is predicting the values based on different interpolation techniques at a regular interval. So, it will fill the elevation values for each cell of a grid, because otherwise you do not have the data at a regular interval, and it can be used to predict unknown values for any geographic point data such as elevation, rainfall, chemical concentration, noise levels and so on. So, the elevation, instead of elevation value, you can have various types of value, and that is why the concept of digital elevation model is very popular and highly useful as well. Now, rationale behind spatial interpolation is the observation that points close together in space are more likely to have similar values than point far apart, and this is based on the Tobler's law of geography. And also we know in our day-to-day life that we will have more influence of those things which are close to us. We will have less influence of those values which are very far from us. And so that's the Tobler's law of geography, that the points close together in space are more likely to have similar values than those points far apart. So when we go for interpolations, all interpolation techniques will avoid this Tobler's law of geography by getting more influence of neighboring points than far distance point. This is the example here, that randomly distributed some elevation points are here. Using these points, a regular grid or a digital elevation model can be created. These lines or this grid of lines and rows and columns are just shown for our understanding, but in a real digital elevation model, boundary of each cell or boundary of entire DM is not really there, except just for our understanding, this grid of or wire mesh has been used here for our But after interpolation, what has happened, that for each cell now we are having elevation values, and therefore we say this is the discrete data set and this is the continuous data set, because at every location we are having some elevation value. In the vector data or the point data set we do not have, and once we are having values for each cell in a grid, then patterns, anomalies and other things can be revealed. More real example here is that the randomly distributed points are here, and then a surface has been created here. If you recall the definition, we said within the observation points, and here the observation points are marked by this rectangular area. So within this point the interpolation is done, but if there are no observations here, like especially here, still the interpolation is done, but that is because on the other side we do not have any observation. So for this area basically it is extrapolation. So when we do the interpolation, though we call as interpolation, but it is a mixed, and as also mentioned that the boundary areas on the edges of our observation or edges of our output DM, we are also having extrapolation. And this information is useful when we go for areas which are having arbitrary boundaries. There we have to take some care about this extrapolation and interpolation. So in subsequent lectures these intricacies will come and we will discuss. Now what basically these surfaces are, that these are different interpolation techniques which we employ, and the differences in methods used for these surfaces are represented here, or we will be discussing that each representation is useful in a specific situation. That means one interpolation technique, all are spatial interpolation techniques. So one interpolation technique may be useful for a terrain like Himalaya, which is highly rugged terrain, or the same technique, same interpolation technique may not be useful for Indo-Gangetic plains, which is a almost plain area, very smoothly undulated terrain, if at all there are changes in elevation. So two extreme terrains are there, same interpolation techniques cannot be employed. What I am trying to say, that if I am having point observations for Himalaya terrain, what I am having point observations also for part of Indo-Gangetic plain, I cannot employ the same interpolation techniques to generate digital elevation models, because the terrain characteristics are completely different, and therefore the prior knowledge about the terrain, about the data set has to be there to choose appropriately a interpolation technique. later also we will be discussing how to check or how to find out that which interpolation will suit my data set as well. So, that we will see little later, but here this is very, very important that depending on the terrain conditions, we have to choose appropriate interpolation technique. And grid representation, that is through the DEM, the surface is considered to be a functional surface because of any given xy location. It stores only a single z value as opposed to multiple z value. So, the attribute of a digital elevation model is only one, and that can be in case of a typical digital elevation model, that can be elevation value. In other cases maybe a water level value or a water table value, or can be a concentration of chemical quantities. And these functional surfaces are continuous, as we know this one. Now, functional surfaces can be used to represent terrestrial surfaces that depicts the Earth's surface, maybe moon surface, Mars surface, because for these areas, or for a planet like Mars or a satellite of Earth like moon, these digital elevation models have been generated. Or also these functional surfaces can also represent statistical surfaces which describe the demographic and mathematical surfaces that are used on arithmetic expressions. So, various techniques are there. The surface representation in its simplest form is done by storing x, y, z values that defines the location of a sample, and this is a typical digital elevation model. In case of contour line representing elevation, it is a line drawn on a map that connects points of equal elevation, and above a datum that is usually represents above mean sea level. So, this is what we get through the these topographic maps, that contours lines are there which are representing the iso heights, and these points can be used to create surfaces. So, from discrete we get the continuous data. Also, we can create using these points a tin surface that is more close to vector data structure, and which can store and display surface models, that we will be also seeing in this course. And tin basically what it does, it partitions the geographic space, the given area for which you are having the point observations, using a irregularly spaced data points, each of which x, y and z values, like in a typical digital elevation model. But here, instead of having a square unit, here the unit is triangle, and the size of each triangle going to be different. Whereas in case of typical grid based DEM, the size of all cells is going to be the same. So, this is major difference here. So, these points are connected by edges in case of tin that form the contiguous non-overlapping triangles and creates a continuous surface that represents the terrain. So, terrain can be represented, earlier we used to have simple contours, which also is a way of representing topography, but it is discrete. Terrain can also be represented through the interpolated surface using point heights or contour values. Through interpolation we can create, or through tin as well. So, there are various methods of representing terrain. The undulations, ruggedness of the terrain can be represented by all these models. The grid is a spatial data structure, we know, that defines a space and an array of cells of equal size that are arranged in rows and columns. Remember this, that each cell is equal within a data set. If it is representing 5 meter by 5 meter ground area, then all the cells will be representing 5 meter by 5 meter area. Whereas in case of tin, all triangles can be representing different sizes of areas. So, that is why it is irregular triangles. It is not regular triangles are there, but in case of cells all are having equal size. In case of grid that represents a surface, each cell contains an attribute value, And raster will always have one single attribute value, whereas in vector, as we have learned in GIS course, can have n number of, theoretically n number of attribute value. But raster will have only one attribute value, and generally we assign z value. Now this z value, depending on our requirements, can be elevation value, concentration value, depth value, or any other thing. And the location of cell in geographic space is obtained from its position relative to the grid's origin. This is the one example here, that here we are having points data, though it is given at a regular interval, whereas we can create contours using point data through again interpolations. Also we can create, using the same point data, a grid, that is a typical digital elevation model, or using the same point data we can also create tins. So three products which we are seeing immediately using point data through interpolations. One is contours, another one is a surface, that is digital elevation model, and third one is a tin. Tin is also surface, but the data structure is entirely different than typical raster DM. Now the question is why to interpolate? Because it is not possible to visit each and every location in a study area. So we go for a sampled, and when we go for sampling or collecting ground information, it is not generally done systematically. Wherever the accessibility is there, we collect that information, and using that information later on through interpolation we can create a continuous information. So the study, visiting every location in a study area to measure the height, magnitude, or concentration of a phenomena is usually difficult, expensive, or maybe in certain conditions impossible. And therefore we would like to have a certain technique to have information about those areas which were not visited at all, and that is only possible through spatial interpolation technique. So instead, strategically dispersed sample point, input point locations can be selected, and a predicted value can be assigned to all other locations. And these are the estimated values. Remember, these are not measured values. Only we are putting measured values to create these estimated values. So measured values are always there, but only for selected locations. And input points can be either randomly or regularly spaced points containing heights, concentration, or magnitude measurements. We continue on this, that as we have seen about the assumption, and the assumption is that makes the interpolation a viable option, that spatially distributed objects are spatially correlated. In other words, we can say that things that are closer, Tobler's law of geography, that the things that are closer together tend to have similar characteristics. And a typical use of point interpolation is to create an elevation surface from a set of sample measurements. Two basic types of interpolation techniques which have been implemented in GIS for creating a digital elevation models, which are based on mathematical functions. One is a linear interpolation, and of course is the second one is non-linear. So linear is little in that sense that it predicts easily, but it has got limitations. So people go for non-linear as well. Now, for example, in the case of linear interpolations, if for where the question mark is shown, we do not have the information, but we are having two informations on each side. So then it becomes easier to estimate if this value at the center using the concept of linear, and that things are linearly related. If we assume this thing, then it becomes very easy to predict the value, that probably the value might be going to be 135. But if things are not related linearly, then it's a different scenario, and then we go for various types of nonlinear techniques. So surface changes in a linear fashion, we know this thing, can use simple mathematical functions while doing linear interpolations. There are some areas where linear interpolation is preferred over nonlinear interpolation, which we will also touch upon this. So, point based interpolation used for data which can be collected at point locations and for example, weather station readings for maybe rainfall data, maybe temperature data, spot heights, soils, groundwater levels, measurement, etc. All these can go here. The example of a typical linear interpolation technique is called Thyssen polygon, and this is called also exact methods, which is input is points data are there, and we do the interpolations assuming things are linearly related, that is through Thyssen polygon concept. It is a proximal, local, exact, abrupt and deterministic. So, all possible things are there. One example here is this is the input data, and this is how these Thyssen polygons are formed. So, in between, like if I take the example here, then at equal distance a line is drawn. Again here between these 2 points at equal distance a line is drawn. Again between these 2 points a equal distance line is drawn, and likewise a complete polygon is formed, and that is Thyssen polygon method. When we did not have the very good non-spatial or non-linear interpolation techniques for rainfall data, many people used to go for Thyssen polygons. So, assuming that within one polygon it is having the same rainfall value, but as we know in nature it is not correct always. So, choosing a appropriate interpolation technique will depend on for which phenomena we are going to use it. And nonlinear, again it is based on the Tobler's law of geography. Points close together in space are more likely to have similar values than points farther apart, and we can also involve a technique which is called distance weighted interpolator or inverse distance. So, closer the point will have more influence on the estimation, and points which are very far will have less influence. So, distance and the technique very popular, one of the very popular nonlinear interpolation technique is called inverse distance weighted IDW. It has been implemented in many GIS softwares, and in which this estimates the cell value by averaging the values of sample data points in a neighborhood of each processing cell. Now, this neighborhood can be decided either using a search radius or number of points in the vicinity, and those things can be used. So, closer a point is to the center of the cell being estimated, more the influence will have, or weight it can be while averaging process. That is why it is called inverse distance weighted. It is a weighted average based on the distance. Less distance, more weight, more distance, less weight. That is why inverse word has been also been. This is the one example. In IDW interpolation assumes that variables being mapped decreases in influence with distance from its sample locations, and for example, when interpolating a surface of pollution, a more distant location will have less influence of a pollutant. This is how it is done, that for the area which is a location which is marked as with a question mark, this will have maximum influence or more influence from point A, which is having value 20. Instead, it will have it will have the least influence from point D, which the value is 200. Though the value is high, but the distance is more. So, in inverse distance, less distance will have more influence on this value. So, first the distance from each neighboring point is measured. So, for wherever the value has to be estimated, the distance from each neighboring point is measured, and the number of points to include in the search can be selected. As I have said, that the search can be either based on the points and also can be on the radius. This I will demonstrate to you through a software as well later, and then the distance is calculated according to a formula. For example, here this is the example from a very popular GIS software which is ArcGIS, ArcMap, and here some soil sample data is being displayed, which is randomly distributed, and the method of interpolation has been chosen is IDW. And here what we are seeing that the pH value for we are considering as a Z value for creating a surface, and the number of points which will be searched around a unknown point are in this particular example are 12. Though you can also, instead of this search, you can have a search based on distance as well. That means a radius you will decide. So you assign power, that means more influence or weight you can assign, and that is the power controls the significance or known points on the interpolated surface values based on their distances from the input. Higher point power means emphasis is placed on nearest points, or resulting surface will have more detail. So you are assigning more weight to neighboring points rather than far distance point. And other one is the search radius, that the less number of points for each cell calculated to improve processing speed. So if you put more search points, that it will take more time to search, it will do more averaging to the point. Again, it depends on for what you are going to use this interpolated surface or a digital elevation model. So accordingly you will choose these, but in default in this particular software the power is given is 2, and the search radius or number of points which will be searched in neighborhood are only 12. Though you can change it, or you can use the distance for such radius. And the third, which is very important here, all techniques will not support this one using the barriers. Barriers can be supplied in form of polylines. By barriers, because if I am creating a surface and I know I am going to use for groundwater related things, then I want to put the drainage lines or river network, because they will influence my groundwater surface. So I will consider as here the barriers. Maybe a geological structure, maybe a fault or other things I can supply while doing interpolations in a polyline file, and that will use as a barrier, because faults may influence the subsurface conditions or even on the surface conditions. So these barriers are important. All techniques will not support barriers, only few techniques will support, especially IDW is supporting these barriers. So barriers is a polyline data set used as a break line that limits the search for input sample points. And if you see that with barriers, this is how a terrain in 3D will look, and sometimes the escarpments which we see on the land surface, sudden change in the elevation, and these are nothing but the barriers. So these can be represented if we know the location of the barriers and supply in a form of polyline file. If I do the interpolations without barriers for the same terrain, this is how it will look. So the with barriers looks more realistic, this one looks more synthetic. So one has to be careful while choosing a particular interpolation techniques and barriers. That information has to be supplied before interpolation. So barrier which reflects the presence of fault lines, cliffs, streams and other features that create linear discontinuity in the surfaces, also control how surfaces are generated. Because if you supply that information, then you can see in this particular example how two completely different elevation models have been created using the same interpolation techniques. The difference is only about the supplying the information about barriers or without barriers. Two techniques, IDW and kriging. So IDW we have just seen here. We will also see later the kriging supports the barriers. Other techniques like Spatial and other interpolation techniques will not support barriers. So again, if if your terrain is having such features, then you are bound, you should be using either of these two techniques to incorporate the information about barriers. This is about the search points which I have been mentioning, that the search, if you say that 12 points around a unknown location have to be searched. So, only those points will be searched, but the same way I can constrain the system that search within the fixed radius. So, either you can give a radius, and then in that case maybe 2 points might be searched or 5 points may be searched. It depends on the density of point observations. So, depends on again your requirements, and you both options generally are supported by most of interpolation techniques which have been implemented in standard GIS softwares. The characteristics of an interpolated surface can be controlled by limiting input points. More the points you incorporate while doing the estimation, more smoother surfaces will create, however it will take more time. So, points can be limited by specifying a maximum number of points which will select the nearest points until the maximum number of points is reached. And alternatively, a radius can also be specified in mapping units. If you are working in a degree decimal, then you have to define this distance in degree decimal. If you are working in meters, then you have to define in meters. Now, if I go for another technique which is called spline, then the options are different. Now, here I can have regularized grids, again I can have different weights, number of points to be searched, and so on and so forth. Now, regularize and tensions. Regularized methods creates a smooth gradually changing surface which values that may be outside the sample data. So, if I am having prior information of the terrain or the phenomena for which I am going to create a surface, then accordingly I will choose these options, either regularize or tension. Tension methods control the stiffness of the surface according to the character of modeled phenomena. So, knowledge about the phenomena is very much required. And third, non-linear interpolation technique which is very popular is kriging. Because the advantage with kriging, it also simultaneously creates a error surface. So, we know exactly how much error while interpolation is being done has been created. So, that is the biggest advantage. We will see in detail that kriging is a group of geostatistical techniques to interpolate the value of a random field, maybe elevation z value of a landscape as a function of geographic location at an unobserved location from observations of its value at nearby locations. And the basically theory behind this interpolation and extrapolation by kriging is that which was developed by a French mathematician Georges Mathron based on a master thesis of Daniel Craig. So, based on his concept, this technique was developed, and therefore, the name has also been given kriging. So, kriging is stochastic, that is something random, also it is exact, smooth or abrupt, global or local. So, it encompasses various kinds of surface representation. If we see in a section or in a profile, what we find that through kriging we may be having a interpolated surface like this, but at 90% confidence interval we may have a surface which is going above this line or 5% here and there, and another way also we can have a surface. So, with the 95% confidential interval we can have these surfaces, and the input are these observations are there. So, depending on what we are what is the phenomena. So, natural data are difficult to model because using smooth functions the normally random fluctuations and measurement error combined to cause irregularities in sample data values, as we can see even at 5% 95% confidence interval, two completely different surfaces can be created. So, here now kriging was developed to model those stochastic concept, and which is based on the concept of a regionalized variable that has 3 components. All 3 together are here, but we can see one by one that one is the red one is the structural component. This may be represented the mean of a constant trend, or a spatially correlated component, that is the data often exhibits positive or spatial correlations, or random noise, which is also shown is through a zigzag file. So, point observation, the data is here, the structural trend is there, then you are having the spatially correlated data is here, and then random noise, and this noise is the measurement of errors, and that is the advantage of having kriging. Kriging can give you error surface, and that lets you know that where errors are there while interpolation has been done. No other methods can estimate errors while doing interpolations. So, what are the components of a regionalized variable? As I have told you that the same display can be splitted, that is structural component, then spatially correlated component, and third is the random noise, which is a non-fitted component here. So, all these components are there in a regionalized variable. If I take the example of a latest version of ArcGIS ArcMap 10.5.1, this is how a GUI for kriging, when you will choose from toolbox kriging method, these are the things which you can use in a kriging. You have to provide a input point feature file or point file, you choose through among the attributes which attribute you want to consider as a z value, then where you will store the output surface, then 2 methods, ordinary and inversal, these are there, and then semi-wavegram models are there, spherical and many other options will be available. What should be the size of cell, that means that you are now fixing here spatial resolution of the digital elevation model which is going to be created using kriging will be here. Then number of points during the search, again by default you are getting 12 values, you can reduce or you can increase. More the search points you will ask, more the time it would take, more the smooth surface it is going to create. Whereas if you are having large distance, the same thing, it will take more time, more smooth surfaces can be created, and finally you can have you can store your results as well. So, this is how a typical kriging interface input are required while creating this one. One of the very useful outputs from kriging analysis is the uncertainty surface that can be generated, and this allows us to answer major question, how good are the predictions, because other techniques do not support this one, the error surface, or in very crude terms you can say error surface. For example, one can create an ordinary krig map and a map showing the standard error of prediction, and we can compare, say for example with a 10. So, here using different techniques, an example is shown that using the same data point data sets, same data point and data has been used while creating a surface using IDW method, then here a spline method and the kriging method. You can see that how completely different surfaces have been created using 3 completely different interpolation techniques. Though IDW and spline are producing a little closer surfaces, but kriging surface is altogether different. Now, there will be a question that if I am having a set of points, I want to do or create a digital elevation model, which interpolation technique should I choose? And that is very important, because we do not know, because everything is being estimated or predicted. Whether predicted surface is close to the reality or real surface, how we will check? So, there are some methods which we will be discussing later, that these can be employed in a very simple way to check which interpolation technique is more suitable for my input data set. And there once you have decided, then for entire data set you can do that one. If we continue on this, if we instead of seeing surfaces like here, if we see a profile of all these three surfaces and also locations of observation points, point data is also shown. What we find here, that IDW is the surface is going like this in this schematic, and whereas your this S-spline surface that is in yellow color is absolutely fitting with all data points, and whereas your kick surface is going above and lower of these. So, depending on the data and the variables which you have choose in different or respective interpolation techniques, your surfaces will be created. Now, what are the problems of interpolation? The problem, the first one, as we have already discussed in little briefly about the accuracy. How accurate this surface which I have generated through a set of points using a particular elevation model, interpolation technique. So, that is a main question. This will be all the time when you produce a interpolated surface, this question can be asked. So, accuracy assessment has to be done. There are ways, either you imply the differential GPS data to check how interpolation is done, or compare your data with maybe a same resolution digital elevation model, or maybe a little higher or lower spatial resolution model, and through which you can check, or already using the input data which you have used, for which the data observed data were there, you can compare with that and can find out that how the best interpolation has been done. Visual in representation can also be used to see this problem, and this is a quick assessment of part of that one. At some time back I told the edge effects, because at the edges you do not have, beyond edges you do not have the observation, and therefore on edges or margin of your data set or boundary of your data set you are creating interpolation, extrapolations, and that extrapolation might bring lot of errors. So, the best solution to this problem is that if you are having your area is not as big as your observation points, then do the interpolation for entire set of points and then extract the area of your interest, and by which you can avoid the extrapolation. So, this is one quick way of nullifying this edge effects. We will be seeing also through software the demonstration by creating a DEM using different interpolation techniques. Also we will be seeing the concept of extent of interpolations, that means the edge issue, and we will try to compare different techniques which we have already discussed. Also when we go for interpolations, we will also see the issue of barriers. So, in this demonstration of the about this discussion which we had about how to create a surface or digital elevation model using point data. So, again I am using this ArcMap and ArcGIS software. Here we have to use some tools which are available within this software. So, when we install this one, a spatial analyst extension is also installed. So, I will be going to that, and then interpolation options, and say for example, if I go for IDW, so I am going for IDW. We are already having a point data. So, now I will take the point data here, the file, and one of the fields which I will use, numeric field, which I will use for interpolation. So here I am, because this is soil data, so I am going to use the pH, because as mentioned earlier that in digital elevation model or terrain model or DSM, it is not necessary that all the time we should have the cell value as elevation value. We can have any value, even a pH value or a electric conductivity value or a pollutant value. So concentration of pollution or any other value. So that is why deliberately I am taking example where instead of elevation we are taking a pH value, and rest of the things are here. I can also control the resolution of a DM which it is going to be generated through this interpolation technique. So for time being I am taking only whatever is a default. Also I am using the default power, because if I increase the power it will take more time and it will create more smoothened surface as discussed earlier. Now here in the default the search points are 12, because it's not a very dense data, it's not a big point data set. So this one is sufficient here. The search radius I can fixed or I can have a variable. So I am going to have a variable. Now in this IDW also allow us to use the barriers. For time being, because it's a soil data, so no requirements of barrier, but if it would have been a groundwater surface data, water table, then barriers will play a very important role. Or it would have been a surface data, and in case of runoff studies, if you are having dikes or other features, faults, then barrier input is very much required. So if I go there and accept all these options, go for interpolation, it will be doing now interpolation. Good. What happened? So now it has as you can see, it has created now interpolation only up to the extent here is only up to the extent of our point data set, because this is what we have chosen. If we go for extension which is say whatever in the view, then it will extrapolate the values there which are going to be definitely very wrong. Now how good interpolation is by this IDW, and especially with this data set, this can also be checked. If we go for this thing and say I just want to search that what happened to these input points against the new values which have been created through the generation of a digital elevation model. So when I go here, I can search all two layers together. So I am going for all layers selection, and now when I click here, now it tells me that in the original value was 20, and this the value which it has the original value was 8.2, and the interpolated value is also 8.2, as you can see in this DM. Name of the DM IDW undercodes shape 1. So this is the input value which is 8.2, and the interpolated value is also 8.2. Let's see some other example here. For example, here the pH value is 6.5. Also it is also 6.500. So quite close to that one. So if I check another value, it is again 6.4, 6.40042. So it is very close, and therefore for such type of data, what we are finding that this IDW interpolation is quite good. Now let's try some other interpolation. So what we will do, we will try switch off this one, take this one again, and say I go for SP line. So again here same data set, same field I am going to have, so that we can compare. and the cell size I am also keeping same. Here instead of tension I am going to have a reguli, but this is optional, and also we can assign the weight here. Weight is already assigned 0.1, it is sufficient, and the search radius and this much. And further, if I want if I want to go the search radius, or want to change, again I can change, but I am not going to do it. So let's go for spline. By the same field Z value, for Z value we are using the same field, and then later on we can compare. Here it has created for spline as well. So now we can see the interpolation done by two techniques and our original points. So let's go back and see that if I click here, what it is telling, that this is my original input. The point data value was 8.2. Through spline I am getting again 8.2, and also from IDW I am getting. So in that way, for this particular data set, let's check another value. This value is also here this value is input value is 8.2, interpolated value in spline it is 8.2, but in IDW quite close, 8.199. Let's check some other values also, and some other input values we will see here. Like for example, one value is here. So if I click on this one, I get 6.4, that is my input value. IDW, through IDW interpolation, again 6.40042, whereas in spline it is going little away and it is 6.38. So if we round off, it would be 6.39. So quite close. So for a small data set, and if values are not varying too much, means the input values or the values in that particular field which we are considering for Z value, then it is likelihood that we will get interpolated values as well, close to the original values. So by this also we can see that how it is looking something that way we can check very well, and overall also this is the overall DM using IDW. This is IDW and this is spline, and the color scheme is also same, but the range, since in this classification the ranges are different, therefore when I click one after another, there are two different patterns are coming, but probably the data wise it is almost same. In this spline, as you have seen, that the spline doesn't support the barriers. So barriers are supported by limited interpolation techniques, example like IDW, but the barriers are not supported by all interpolation techniques as given here. As you can see that in this particular software, IDW is supported, kriging is supported, and natural neighbors are, and this one is common for other, and then spline and some other trend surfaces are also there. So in this particular lecture we have in the beginning we have discussed various types of interpolation techniques, but in this one basically we have focused how this using a topographic maps or point data and employing a spatial interpolation techniques and different techniques by which we can create digital elevation model. So thank you very much.